I will talk about beating heart simulation driven by three-dimensional molecular dynamics model. And though it is not listed in this author, so many of works are also giving from the joint work with Fujitsu people. And so at the start run of K-Computer, we had a chance to use the whole system to simulate 1.5 beats of multiscale heart, in which 3 levels, heart and cell and contractile proteins are modeled and simulated. And also, along with the mass dynamics, its interaction with coronary circulations also simulated. And the micro level, the sarcomere dynamics involving nearly 160 motor proteins simulated by the Monte Carlo simulations. So the Monte Carlo simulation is applied to simulate the stochastic behavior of molecular motors. And these distinct sarcomere models were embedded into 5 kilo myofibril elements in the cell model, which is a finite element model. And this finite element model embedded into the 600 kilo elements in the ventricle model. And this application, in this application, so in this implementation, this heart cell model is assigned to 1 core of K-computer, so there is no communication and synchronized overhead up to this mesoscale computations. And this mechanical problems is dealt with nonlinear system and solved by Newton-Raphson iterations. And this involves 50 kilo degrees of freedom, and the most of ship computational floating point operation is occupied by sparse LU factorization to solve linear system among all of the computations. So we have achieved nearly 2.7 petaflops, which was nearly 30% of peak. Though such a huge application is is unrealistic for daily clinical applications. So later on, we have applied the developed numerical techniques and molecular models into the real clinical application by skipping the mesoscale heart cell model, where we directly embed the sarcomere dynamics model into the element of the macroscale model, where the strain change in the fiber direction is sent to the microscale, and it is reflected as sarcomere length change. And this length change affects the load of the protein motors, individual protein motors here, and it affects the lever arm swing behavior and the detachment event. So in this way, the macroscale movement affects the microscale molecular behavior. And on the other hand, the total contraction force of sarcomere model is sent to the macroscale, and it is used to compute the active stress tensor, which drives motion of macroscale model. This is one real applications, which is the prediction of post-operation of congenital heart disease. In this patient, there is a hole in the septum which must separate left ventricle and right ventricles. And the aorta is connected to the right ventricle instead of left ventricle. So the mixture of arterial and venous blood is generated here and sent to the aorta, and the right ventricle is forced to work under the extremely high pressure than usual. And here, in this case, we simulated the effect of artificial blood vessel here, which connect the hole to the aorta. And with this operation and our evaluations, of course, we can separate the blood completely, and we reduce the blood pressure of left ventricle to the normal values. And we have also evaluated the energy consumptions here and there is a big reductions of energy consumptions of right ventricle here. And such energy consumption is evaluated by counting the detachment event of molecular models from its LIGO state. So these experiences reminded us the needs of further developing more detailed, applying more detailed three-dimensional molecular model to our applications. So in the post-K computer, we are trying to develop a coupled platform with more detailed 3D molecular models. One research direction is instead of applying 1D Monte Carlo model, so we develop by ourselves a super coarse-grained molecular model. And instead of this Monte Carlo, we apply such a potential profile for lever arm swing, and these depths of wells and barriers directly control the lever arm swing for this molecule. And here in this animation, we reproduce the spontaneous oscillation by our models, where this spontaneous operation is given from some kind of reversal, avalanche of reversal power strokes. And I think this is a very important cooperative property of molecular motors to realize very quick relaxation of cardiac muscles. And in second direction of our approach is using more detailed 3D molecular model, CAFEMO, which is developed by Takada Laboratories in Kyoto Universities. And from these approaches, we expect that we can analyze the relationship between heart disease and the genetic mutations of molecular motors. And in this approach, currently, we apply the switching potential strategy between such several states. And for this switching, we use CAFEMO. And we evaluate the switching probability by observing some deformation called nucleotide binding site inside of these head regions in this approach. And here, I show you very preliminary our version where we couple this ring model with the CAFEMO. And this is very simplified model of beating heart, in which we have 6 finite elements. And so in each element, the filament is arranged along circumferential direction of this ring. And in each element, the filament slides to the center, and the thin filaments are connected at the boundary of edge. And this shows, because it's synchronous, this shows very well the relationship between the blood ejection and the dynamics of motor proteins. Here, so along with the shortening of sarcomere, this element shrinks. And so the transmural width also increases due to incompatibility of this material. And with this movement, the blood inside is pushed inward effectively. And in this contraction phase, this high pressure inside of this cavity should be supported by very strong contraction force here, which should be nearly almost equal through all elements. So the difference between the activity of each element should be compensated by some instantaneous length change of these sarcomeres. Here I show some history of the shortening of this sarcomere. Of course, in the contraction phase, it increases gradually, but you can see here, so it includes also a lot of back steps. And in this animation, I show you this color of blood shows the pulling force. And this red color shows the positive force, and it contributes the contraction of this filament. And the negative shows negative pulling force, it's hampering the contraction. And so in usual cycle, with this lever arm swing, the positive force is generated. But with filament sliding, this positive contribution is gradually eliminated. But with these small back steps, the filament elongated momentarily, and the active host increased momentarities. And such kind of environment where these molecules work cannot be provided artificially, and this can be provided by doing simulations in such a whole systems. And here I show you behavior-specific molecules, and in these upper panels, it shows the history of the lever arm swing distances. And these red lines show the state transitions. And this middle panel shows the host, and in these two cycles, so this motor protein failed to make the positive host. And here in this bottom panel, I show you some distances between some specific point in nucleus binding domain to look for some correlation of successfulness of cycle and deformation of here. And actually, if I plot the deformations with respect to these distances for successful cycles with red and unsuccessful cycles with green, I observe some larger population here. So we tested new models where we magnified reversal power stroke transitions by factor 10. And actually, in this new model, in this pressure volume loop of this ring model, even though it is small, we observed a 3% increase of blood ejection. And more interestingly, so this model achieved a 10% reduction of energy consumptions. And of course, this model is just a beginning step of very difficult challenge. But through such experience, I was made to recognize the importance to simulate the molecular dynamics under some environment, which is given by themselves and in some sense in natural conditions. And finally, I will make some comment, briefly introduce some coupling numerical techniques focusing on efficiency and stability of our multiscale approaches. So to hide communication overhead between scales, we applied a multiple time step strategy where plural microscale time steps are performed within one macro time step. And in this application of ring model, so such a computation of macro scale and communications is negligible. It becomes negligible when we perform 1,000 time steps within one macro time step. But in such aggressive coupling, so becomes usually very unstable because we miss some important stiffness property coming from microscale phenomena. For example, if you put force in your muscles, you feel your muscle becomes stiff. And this is because there are a lot of cross bridges here. And if you transfer only the force, you miss such a stiffness, the muscles. So instead of sending contraction force alone to the macro scale, we also send the stiffness and redefine the contraction force by using this stiffness. By doing this, using this technique, we can apply very aggressive multiple time step strategies. Actually, as you can see here, this is the history of the shortening of one element and the strain of one element. So this black line shows the result when we apply the one by one communications by each micro time step. So it's accurate computations. And this red line shows result coming from our aggressive strong coupling technique. And this highly oscillating result coming from aggressive coupling without taking stiffness into account. And so also this energy consumption profile further confirms robustness of our approach. And concluding remarks, so here I introduced a multiscale platform that enables us to analyze the stochastic dynamics of motor proteins under the condition that is generated by the protein motors themselves, and that can't be made from artificial boundary conditions. for this such kind of simulations with using big system is very important. And as for the these terms, to be honest, I have not much experience so far. But of course, with one run, we have many data stored, molecular data, and we have to utilize these data to develop our models. And thank you very much for your listening.